All right, that means delta T would have been negative, and it would have nullified the negative here, which would have made this a positive number. I mean, that would have meant that energy is being absorbed somehow. So the signs take care of itself, but you have to have that sign in the beginning for the first law to take that into account, right? Just to make sure it follows what should make sense. All right. All right, calorimetry, probably the toughest part about this chapter, because it's just the first law, and it's that darn negative sign. All right, so just keep track of the negative sign, you'll be doing all right. All right. So, questions about bomb calorimetry? Okay, from the expressions on your faces, I'm not sure if you think it's the bomb, but anyway, just bear with it. Hopefully, with some practice next week, we'll probably iron that out. All right, so there's also a term called enthalpy. In a nutshell, enthalpy is a fancy term for just saying it's heat. Okay, but it's how we measure heat under a certain condition, and that condition is under constant pressure. Normally, when we burn things in the air, we're burning them against a constant pressure. If you burn firewood or if you burn coal, there's an enthalpy change associated with that reaction, burning coal. You're burning it against a constant external pressure, right? You know, even right near the coal, it's pretty much 1 atmosphere for the pressure. So usually we're burning things in the open air against constant atmospheric pressure, and that heat that's evolved at constant pressure, we have a term for it, it's called enthalpy. Now the equation for enthalpy in absolute terms is this, but we don't care about this equation. What we care about is the change in enthalpy, because enthalpy is a state function. So what we end up getting is this equation instead. So if you say delta H is equal to the change in internal energy plus the work that might be done from that. Okay, at constant pressure, okay, it reduces to simply just Q. Okay, how do we get from here to here? Let me show you real quick. Just do some derivation. So we know that, see, delta H, excuse me, delta E is fine. All right, delta H is equal to delta E plus P delta B. But we know that delta E is equal to Q plus W plus P delta B. But we also know that Q plus negative P delta B is that. Adding it to another P delta B here shows that this minus this plus that gets you 0, right? So ultimately, at constant pressure, delta H is just equal to Q. So the consequence of this result is basically saying, well, now we can measure the change in heat for reactions in an open cup to the atmosphere, and we can use a different kind of calorimeter to measure enthalpy. Okay. So just before we get to that, though, what's the difference between delta E and delta H? Right, so usually delta E and delta H are very similar in value. Again, just to not state just letters, what's the change between the enthalpy and the internal energy change? All right, they're usually very similar. But if you do have gases being produced in a reaction, you might have a significant amount of work that's done, and that difference might be enough to cause a significant change between the two. For example, if someone uses a lighter, butane is burned inside the lighter, right? When one mole of butane burns at constant pressure, okay, imagine someone who still smokes cigarettes. I will say I've seen a lot less people smoke today than I ever have, but which is a good thing. But when someone is smoking, okay, they have the lighter, they light up. Okay, what they don't realize when they're smoking that cigarette is they actually did chemistry. Okay, before everyone else's eyes, they burn that butane in the lighter. The burning of butane in the lighter, okay, lighter fluid, okay, is 2,658 kilojoules of heat that's released, but also a little bit of heat, a little bit of work is done too, okay, because when you're lighting a lighter, if you open up the lighter without actually sparking it, what do you hear coming out? There's a little of the gas coming out, right? So butane, it's a hydrocarbon. It's got a relatively low boiling point, okay, and it wants to just vaporize. And so there's a little bit of gas expanding even while you're lighting it. So that gas expansion does about 3 kilojoules of work. So delta H would be the negative 2658. Okay, that's the heat being released when you light it. Okay, the extra 3 gives you an extra 3 kilojoules of energy that's released. So delta E would be negative 2661, but delta H would be a little bit less than that, okay, which is negative 2658. So just so you have an idea of what's the difference between delta E and delta H, what are we comparing here? Usually they're about the same, they're very similar, but if a lot of gas is being released, delta E might be significantly larger than delta H, but not in this case. Okay. So, just so you have an idea. So, bond calorimeters, they measure delta E. They measure internal energy change, but we have something called a coffee cup calorimeter, which measures only enthalpy. Right? We basically let the work escape. Right? We only measure heat. So, what a coffee cup calorimeter is, it's just a styrofoam cup nested into another styrofoam cup. And it's got an insulated lid on top of it, and you got a little thermometer in there, but it's not gas tight. Okay, it still allows pressure to escape. Okay, so we're still keeping pressure constant, but we have this reaction in solution that's going on. It releases heat. We'll be doing a lab in a couple of weeks that uses this, so stay tuned. Okay. So for coffee cup calorimeters, because the container isn't insulated from volume change, so because we're letting the volume change just happen if it does happen, because we're letting this gas escape if gas is produced, at that point, we use a different kind of equation. All right, instead of using CAT, we use NCAT. So we're going back to NCAT again from Chem 107. But just know that it's only used for coffee cup calorimetry, not for bond calorimetry. All right, so M is the mass of the solution. Typically, these reactions are done in water. So, like, what if you wanted to measure the heat change associated with acid reacting with a base? Okay, and coffee cup calorimetry is ideal for that kind of measurement. So, like, if I was to give you a question on an exam, you want to measure the heat change of an acid to base reacting, what technique would you use? Bond calorimetry or coffee cup calorimetry? What would you tell me? Coffee cup. Okay, well why would you do that? Well, because acid base reactions sometimes reduce gas, but we're only looking at measuring enthalpy. Alright. So here's another example of a coffee cup problem. So a mass of 0.103 grams of zinc metal completely reacts in a 50 milliliter solution of hydrochloric acid. It gives you an approximate density there, and it does it inside a coffee cup calorimeter. During the reaction, the solution temperature rises from 22.5 to 23.7, assuming that the specific heat of the solution is 4.184. What is the enthalpy of this reaction in kilojoules per mole of zinc reacted? So how do I know what equation to use, cat or MCAT? How do I know when I'm looking at this problem? What kind of calorimeter does it tell me I'm using? Coffee cup. So when you're looking at these kinds of problems, okay, when you're looking at calorimetry, look for what kind of calorimeter tells you. A lot of them will tell you coffee cup or bomb. What if instead it said it takes place at constant volume? Which equation would you use? Yeah. So constant volume is a bond calorimeter, so that would say use Q is equal to cat, not Q is equal to MCAT. All right. So what if it said reacts with solution to the open air instead of a coffee cup calorimeter? What equation would you use? Q is equal to MCAT, right? Open to the air means coffee cup calorimeter. All right, so that's really the highlight with calorimetry problems is just knowing which one to use based on the calorimeter that it's telling you. Okay, so we have this reaction of zinc. Now here's a review question for you, maybe for next exam relative to the first exam. What's the chemistry here taking place? If I wrote out a reaction for this process, what would it be? It says zinc metal completely reacts with hydrochloric acid. Yeah, it's a redox. So zinc plus HCl gives me what? Right, zinc, chloride. How do I write zinc chloride? Yeah, ZnCl2, because zinc is always 2 plus when it becomes oxidized. And hydrogen gas. And of course, balancing it would put a 2 in front there. Okay, so it's saying, well, you're doing this reaction inside this coffee cup calorimeter. What is the enthalpy for this? That's what it's asking. What if it said, what is the internal energy change, E? What if it asked for that instead? What if it said, what is the internal energy change, not the enthalpy? At that point, what we'd have to do is we'd have to have some modified equation to take into account the change in volume that takes place when you produce this hydrogen gas. That's a little bit beyond the scope of your textbook, so we won't do that, but I'm just kind of saying it just to see you understand the nice simplicity of just doing enthalpy instead. So we'll just do enthalpy here. Okay, so how do we start this? How do we set it up? What's the first law we always use? The first law. I meant to say first thing, but it came out as first law. It's like my Freudian mind coming out, like, oh, I meant to say first thing, not first law, but it just came out. And that's because we always talk about the first law in this class. So how do I set up the first law? Well, let's look at the last one we did. Let's just set that up. So negative Q of the system is equal to positive heat for the surroundings. Again, that's just a statement of the first law. Remember, I was asking you yesterday, how many different ways can you state the first law? We can say, okay, there's no free lunch. Energy is conserved for the universe. Energy is neither created nor destroyed in any process. You can say negative Q system equals positive Q surroundings. All right, that's another way of saying it. All right, there's tons of different equations we've already used for the first law. Just make sure you have system on one side and surroundings on the other. Okay, so for a coffee cup, there's no work, it's just heat. So what does Q become here? Okay, in the bomb situation, Q became delta E. What does it become here? It becomes delta H. So we're going to say negative delta H system Okay, and what do you think Q is going to become? It's going to become MCAT. So it's going to become MCS T final minus T initial. And this will be for the surroundings. What is the surroundings in this case? It's the calorimeter, but mainly, instead of having specific heat for the calorimeter, instead we use the solution itself as the surroundings. So imagine this reaction happening. Now, when it says aqueous here, that means that there's water all over the place, right? There's this HCl is sitting there, but it's actually H plus ions, chloride ions floating around in solution. And of course, the H plus is just dying to get together with zinc to produce some hydrogen gas. Right, that's what's going on. So think about water as the solution surrounding this reaction that happens. And so this is why we use MCAT for coffee cup problems, because the solution surrounding the reaction, it acts as the surroundings. Hope that makes sense. Whereas with bomb calorimetry, because you've got part of that sealed jacket around the reaction, you have to have just calorimeter for the specific heat for the calorimeter. So for mass, what do we use? It gives us a mass here. Well, it gives us mass of zinc, but the zinc, it's not part of the solution. It's the solid you're dropping into the solution. Is there another way we can find a mass? We can say, okay, density times volume equal mass. Right, so density times volume. All right, and then we have specific heat, which is still specific heat. So density it gives us is 1.0 gram per milliliter times the volume. So 50 mLs times the 1.0 gram per milliliter. Now we get a mass. And this is the mass of our solution. This is the mass of our surroundings. Are you following at all? Maybe, maybe not. So again, the solution around this reaction is what acts as the surroundings in a coffee cup calorimeter. It tells us that the specific heat is 4.18 joules per gram per degree C. And then TF is what? It's 23.7 minus 22.5. So do you see how it's very similar to that setup for the bomb? Right? It's just a different equation to use. Right? So doing all the plugging and chugging here, the right side of the equation becomes 250.8 kilojoules. Excuse me, that's joules, not joules. There I go again. I want kilojoules already. Okay, and we have negative delta H on all these steps here. Right, negative delta H is equal to, in kilojoules, it's going to be actually, let's do this negative delta H system, and we're going to say molar, right? Because it's asking us what is the enthalpy of this reaction in kilojoules per mole. So we're going to say 250.8 kilojoules, or excuse me, joules. Let's do symmetric conversion here. How do we get from joules to kilojoules? Yeah, 1,000 joules in a kilojoule. All right, and then we have on the bottom, per mole, we've got 0.103 grams of zinc. And to get to moles from there, we got to divide by the molar mass of zinc. That's 65.38 grams per mole of zinc. So of course we're left with kilojoules and moles on the bottom. And then that gives us, how many sig figs are going to be in the answer? Well, we have only 2 here for the density. So that means this 5 here represents the last sig fig. So we only have 2 sig figs for our answer because of that. So it becomes minus 160 kilojoules per mole of reactant, which is the zinc in this case. So look at these 2 problems, one for the bomb, one for the coffee. Do they look very similar in how they're worked out? So what I'm hoping that you get to at some point with this chapter, which is very kind of esoteric, I'm sure you kind of feel like you're venturing into new waters here. It's like, hey, wait, this is kind of new, you know, right? But with calorimetry, it's the technique with how we measure energy change in our normal everyday life. Okay, and they're all worked out the same. Okay, and when I say that, I mean they're all worked out starting with the first law. So if you get a calorimetry problem, always go back to the first law. Okay, that's like your bread and butter. All right, set up the negative on one side, the positive on the other. Okay, and then you just work it out from there. So how did I get this negative sign here? Well, because this negative made its way to the other side. So do you think that this reaction releases energy, or do you think it consumes energy? Is it going to produce heat, or is it going to absorb heat? Have any of you done dropped a piece of metal into acid and seen what happens? Well, you will. You'll actually do it next week. So yeah, next week we'll do some of these. Which is rather exciting. I'm excited about it, right? You drop some acid in a metal and some acid. Sometimes it reacts, sometimes it doesn't, and we'll talk about a little bit about why that is next week too. But this reaction will produce some heat. It's going to release some gas and some heat. Okay, it turns out. Okay, so coffee cup, bomb calorimeter. You can see they're kind of worked out the same. They start from the first law. The only difference is that with bomb calorimetry, you use CAT. With coffee cup calorimetry, you use MCAT for the SRABIs. And that's calorimetry in a nutshell. All right, and this next slide just describes that. All right, just tells you MCAT or CAT, depending on which calorimetry you have. So how do you feel about calorimetry? It's not easy. It's still going to take some time. We'll try to do some problems next week with calorimetry. Quell your fears if you have them. Okay. And this is another slide kind of describing, what's the difference between measuring delta E versus delta H. Again, delta E is measured in a closed system. It's a bomb calorimeter. They do that to make sure that they can include that work in the heat that they measure. Delta H is measured in an open system, which is just a coffee cup calorimeter. All right, and then in both cases you're measuring heat. Ideally, it'd be nice if you could measure both to estimate the work that is done, but it doesn't quite work that way because, again, with the coffee cup versus a bomb, they're measuring two different things. And in a coffee cup, you're measuring solution phase chemistry in solution. With a bomb calorimeter, you're measuring a solid. And you're burning a solid in a closed container. So it's kind of hard, you know, to measure everything with the same technique and compare and contrast. But so the two kinds of calorimeters are used in a different context. But here's the thing: the work done by a system usually is of little interest to us. So usually we're really more interested in just measuring delta H instead. So most of the time from here on out, after the calorimetry part here, you'll be looking mainly at just delta H, right? What do we measure with a coffee cup calorimeter? Next semester in Chem 111B, you'll be combining enthalpy with another state function called entropy, okay? And entropy is the disorder a system can cause, and you combine that with the heat and you get something called Gibbs free energy, and that is the ultimate gauge of spontaneity of chemical reactions. And so you'll get that next semester, and it turns out that coupling Gibbs free energy reactions in our bodies helps regulate our metabolism. So it's really cool stuff. They may not talk about that, whoever you have in that class, but in biochemistry they taught us about that. It was really cool. All right. Okay, so any questions about bomb versus coffee cup? What are you measuring? Delta E for bomb, delta H for coffee. Solid phase for bomb, solution phase for coffee. Okay, that's basically what you're looking at. This gets us to another important concept, which is what's exothermic versus endothermic. If you had biology before, they use the term endogenic versus exogenic. Did they use that in bio?